Spring break started today. They just decided to shut the class.
All right. Okay, that's okay. All right, so we'll go ahead and take a look at the homework assignment that was due today, and just to show you guys how to work on it. Or do you guys think it's not necessary? You guys got it already?
I would like to see it.
You would like to see it? Okay, good, cool. We'll do that. All right, so this is the assignment itself. I'm seeing that I'm saturating my mic occasionally, so I'm gonna change the mic setup a little bit. Okay. And let's see, it is input devices. Yeah, so I usually have it set to right here, but it might be too soft, so maybe right there. I think that looks good. There we go. Okay, so we will take a look at the homework assignment. I'm just going to copy and paste, oops, just that into a notepad or mouse pad, and then we'll work on this. All right, so there are two questions, okay? So make sure that you go through two different resolution and proof process. So this is what is given to you. It is the end or the result of the previous homework assignment. And this is the first question, and this is the second question. So there are two parts to the homework assignment. So we'll go ahead and get rid of all the stuff that is not really needed, okay? So this is the theorem. The theorem is, or the proposed theorem, is that P implies S times R, or S and R. So the first thing we need to do is to convert this into a negative first, and then convert it into a CNF, okay? So now we have to look at the negative theorem. So the negative theorem is really just the negation of whatever the theorem is, okay? So now we have to convert this a little bit, and first we apply the definition of implication. So that would be the negation of the first part or the second part, okay? And then we look at this and go like, we can definitely apply. You can do the distribution first, or you can apply De Morgan's law first. It doesn't really matter which one. So I typically like to apply De Morgan's law first, which means we have double negation of T and the negation of SR. Okay, so we cannot just simplify this and go like, oh, okay, we can just dissolve the parentheses, because the negation is applied to the conjunction and not just to S itself. So we cannot just dissolve the parentheses. So this becomes just T, and then we apply De Morgan's law to the other part, which is not S or not R, okay? And then at this point we can use distribution, which ends up with, nope, we don't have to do distribution anymore. This is already in CNF. Okay, so this is a CNF formula. There we go. Okay, so now what we need to do is to combine what we already know, which is this part, with the negative theorem. So we have T as one thing, and then not R or not S is the other one. So you look at this and you try to resolve, right? So you look at the first term. So I do this usually kind of systematically. I look at the first term and I ask, can the first term resolve with any other term? The first term has not Q. Is there a Q somewhere? Nope. It has not R. Is there a R somewhere?
Yeah.
No. It has not S. Is there a S somewhere? Nope. Okay, so the first term cannot resolve with the other three terms. We look at the second term. We don't have to look at the first term anymore because we evaluate the first term already. So when you look at the second term, you only have to match the second term with the third and the fourth term. we have not Q, we know there's nothing to match it. Not R, we know there's nothing to match it. So we look at T. Is there a not T somewhere else? Nope. Okay. So that means the second term cannot resolve with anything else. Then we look at the third term. It can only resolve with the last term because the third term is the second last term already. So this is T, and we ask, is there any not T in here? Well, we kind of asked that question already. There's no not T. So that means there's nothing you can do, absolutely nothing you can do about this CNF. So that means, well, since you cannot resolve, okay, so we basically say no resolution is possible. So the theorem, the proposed theorem is not a theorem. Okay? So the conclusion is not that the proposed theorem T implies SR is not true. It is just, it does not follow whatever was given to you as to be true to begin with. Yep.
I guess what I did is I did distribute from there, and then I broke it up into again, I guess, to get it into, I mean, is that wrong?
That would not be resolution. In other words, you started with this, right?
No, from the T and not S or not R, I guess the third line, the last one where you
This one?
Yeah, I distributed that. And then
But if you distribute, then it's not a CNF anymore.
But then I did, I guess I did it again.
Oh, okay, yeah. As long as you get to the end result.
Alright.
Yep. Did you end up with something like this? You should still end up with this, though.
Yeah.
Okay. So you just took a
That's
slightly more
that's
scenic
what I
route.
didn't need
Yeah.
to.
It's okay. It's not a problem. Scenic routes are fine.
Practice.
Yep.
Yeah.
It's perfectly okay. No problem. All right. So the second one is this is our theorem. So it's kind of important to identify what the theorem is, because then you can talk about what is the negated theorem. So in this case, the negated theorem is just QR. The negation of QR implies T. So the first thing that I do is I just expand the implication or replace the implication with its own definition. So that becomes the negation of QR and or the T, because we have to negate the first part and keep the second part. And then we apply the Morgan's law, just like the other one. So now we have QR because of double negation, and then we have the T, not T over here, and I think
That's CNF.
Huh?
That's it, right?
It is a CNF already. Now, because this is already a CNF, this is misleading because it has extra parentheses here. So I personally would either turn this into QR not T without the parentheses, or I would introduce a pair of parentheses for each term. That is not required. Okay, so if you don't do any of these steps, it's okay. But I would like this. I want to do this before I merge it with a big CNF, just so that I know which part is which part. So I'm gonna put it here, and then we copy this, and you can put it at the beginning or the end because conjunction is commutative, so it doesn't really matter whether you put it at the end or at the beginning. So now we try to do the resolution. So when you perform resolution, you can actually use equal to, okay, because each new term that you're adding is implied by the existing terms already. So you're not really changing the truth value of the overall conjunction. So you can use equal to, or if you want to be more precise, you can always say implies the following, okay? So now we look at the first term, and then we ask, can we resolve this with something else? Now, if you want to do it the systematic way, that's how I do it. On the other hand, if you kind of eyeball this whole thing and you say, okay, I can figure out a really fast way to get to a contradiction, that works too. But personally, I would like to work on something, kind of more systematic way. So I look at the first term, I look at the second term. I know those two cannot resolve, okay. But the new stuff that we add obviously can lead to resolution. There's a Q right here, so so what I usually do is I underline what I begin with, and then I go back and just add the new term as the result of the resolution. So in this case, the new term because of resolving not Q or not R or not S with Q is really just not R or not S. Is that okay? Are there any questions about the result of this resolution? Okay. So I look at the first term again and I ask, can it resolve with something else? Oh yeah, R can resolve with it. So we take the same thing and then we look at R and go like, yep, these two can resolve. So the result of that resolution, oops, hit the wrong key. Okay, copy, paste. So the result of this resolution is going to be not Q or not S, okay? And then we look at all of these terms and go like, okay, can the first term resolve with anything else? Nope, because S is not a term anymore. So now we have to look at the second term. When you look at the second term, it can resolve with a whole bunch of stuff too. So obviously, this, if I work on it this way, it's going to take a little bit of time before I get to the contradiction. So, but if you look at the terms that we already have, you can say, oh, if we can somehow get rid of, let's see, I do need this term to be resolved, right? Because otherwise there's no, I can't get to the end result. So with this one, I will skip the R, and instead I will go straight for the T. So I'm gonna look at these two. Actually, R is fine too. I can look at QR as well, but individually. Okay, so we'll do it step by step like this. Okay. So when you do resolution, it is important not to skip a step. Okay. So this time, I got not R or T left. Okay. And then we look at these and go like, it looks like now we can actually look at a shortcut. Take this one. Take this one. Okay, so copy, paste, and then these two resolves to just not R, right? Because the not T and the T cancel out, and then you concatenate the rest of the expressions, so we got not R left. So at this point, it is quite obvious that we can get to the contradiction just by looking at this one and also this one. So that implies, okay. Now this is the kind of funky part because it implies, after they concatenate, it becomes nothing, but the nothing is really not really nothing. There's a zero in it. In other words, there's a hidden or zero in every single one of these expressions. It's just that it doesn't make sense to write or zero or zero or zero all the time. But when there's nothing left in an expression after the resolution, then the only thing left is the zero, because everything else is gone. So because you resolve to a zero or false, okay, so you basically say because the negated theorem leads to a contradiction, the theorem itself is true. Or the theorem itself, the proposed theorem is a theorem. Okay, the proposed theorem is a theorem. Yep.
So I had a question about, so if you're looking at it kind of like logically from the beginning, and we see that Q is true, or I don't know how to say it. We have Q and R.
Right.
We're not allowed to use those to reduce that second.
In one single step?
Not one single step, but like if you like go through your work, you're not allowed to use those to reduce the second term to like you end up with like not T and T, and then that resolves that.
Okay, so we are looking at the second term and which term again?
I'd say like Q, yeah, Q and R.
These two? You have to do it in 2 steps.
Okay, right.
Yeah, so so I could have started with this one and not pay attention to the first one, but I'm just kind of showing you that the more systematic way, if you were to if you were to write a program to do it, it'll be kind of more systematic and just start with the first term.
Right, okay. Alright. I'll try to look through it.
Okay. Yep.
So I resolve with T at the very beginning, so you get like a not Q plus not
Uh-huh.
times the Q and R.
Yep.
And you do Morgan's law. Is that fine?
It will still take 2 more steps of resolution, right? Yeah. Okay, so let me see if I understand what you're saying. Okay, so in your case, you start with resolving the t, so that means you're only looking at this term and this term to begin with. So that means what you end up with is going to be not q or not r, like that, right? So it will take 2 more steps of resolution to get to the 0, because right now it's not a single step. You cannot do it in a single step, because in every single step you can only resolve one variable with another variable in another expression. So that means this now becomes not r by itself. So at this point you can now resolve the r with not r. Then you get to 0. Is that okay? Did you skip a step?
Yeah.
Okay, if you skip a step, okay, there's one thing that you can do that will still get you all the points. If you skip a step, okay, let me just go from the place where you skipped a step to show how you can actually just do that in one single step. So let's say you're here, okay? So what you do is you look at this expression, and then what you do is you say this is really the same thing as, and then you look at these two or you look at this, and you can basically look at these two and you say one is the negation of the other.
No, that's what I did.
So did you show that part?
Yeah. I did like QR and not.
Okay. So you basically apply the reverse of the Morgan's law,
Yeah.
and then you turn this whole thing into not QR.
And then that.
Then there's a negated term here that is matching a non-negated same term. Then you can do the resolution. So technically speaking, it is not the mechanical way of doing resolution, because the computer is likely to be programmed to only do one variable at a time, and not to apply the Morgan's law first in the disjunctive terms and then look for things that it can resolve. But if you do it this step and it is clear that this is what you're doing, that you're identifying that this thing, okay, not Q or not R, is really the same thing as the negation of Q and R, and then you look, and then you say, oh, there's another QR over here because the conjunction is associative, and you can just put extra parentheses around it. As long as that is clear to me, you can still get full credit for that. Yep.
So I think I see what I did now. So for the second term then?
Second term, which is
group of terms then?
yeah,
And
this
then,
one.
So if you resolve that with Q, then you get not R or T as a result.
Yes.
And then you resolve that with R.
Yep.
And then you can get T and not T
Yep.
as a result, and then you could say that add 0 onto that.
That works too. There are
So
multiple paths.
Right. And then if you did that though, you can't do that in one step, and then you shouldn't do that. Well, you can't do that in one step then, right?
It would be non-standard.
Okay.
Because the standard way to do it is to only deal with one variable at a time, and not to apply the Morgan's law to convert it from a CNF back to a non-CNF.
Okay, right.
Yep.
So we get like, so some points off of that.
It depends on whether it's clear.
Okay.
Yeah. So if it is clear that you understand what resolution is, and you're not skipping any steps, then it will still be okay. In other words, you can start with this, okay? You can start with this and not even having this term here. Okay, so let's get rid of this one here. Okay, so you can start with this and you say, oh, okay, I can apply the following. Okay, so we'll keep it pretty much the same as the other one, and then we'll just do one minor change. We'll perform one minor change. So we'll just say that, oh, I can group these two together. Okay, there's nothing wrong with this. Okay, but it is now starting to become Boolean algebra instead of resolution. Okay, so once you group these two, then you can say, oh, okay, we can see this is the negation of both terms of a disjunction. So I can apply the reverse of De Morgan's law and turn this into the negation of Q and R. Okay, that's another step. And also, within the same step, you can say, okay, because it's conjunction, we can dissolve the parentheses. So now you can say, okay, I can now resolve it because this is a single term. This is the non-negative version of that term. So these two can now resolve. So that would still work. Yeah, because you're...
I prefer the first way.
So this will still get full credit because it is still using resolution, except you're doing some extra Boolean algebra work so that your number of steps of resolution is reduced. Yep.
I'm not seeing what happened to the not S. I'm missing the part where it's getting resolved. I was a little confused about that. So like even on your main solution, I wasn't sure what happened to the not S.
The not S?
So,
It's not used. It's not useful.
okay.
You can do resolution with it, but it doesn't lead you anywhere. So basically, if you go all the way back to here, it does resolve with Q, it resolves with R. So, but the best you can do is to end up with a not S. Then it's stuck because there's no non-negative version of S anywhere. So you will still get stuck with the first term. So the first term is not useful at all in the proof itself. But mechanically, I just go through that motion and go like, oh, it can resolve, except the result of the resolution doesn't help. So are there any questions? Yep.
I'm just curious how strict you're going to be on user input error. I realize that I've made a typo in my submission.
What kind of a typo?
It's in the negated theorem with number 2.
Uh-huh.
I left it as just T, but on my paperwork, I have
Oh,
it
okay.
and then all of the logic that follows treats my T that I inputted as a negated T.
But you will still be able to prove the theorem. Or would you? No. Without the T, you cannot.
Yeah, so it's just
Okay.
that I forgot the negated symbol,
Hmm.
but all of the logic under it follows.
Okay. So you will still get most of the credit because, it's still... The homework assignment is really to see if you know how to do resolution and how to come up with the conclusion at the end of the resolution process. So because of a mistake, you cannot come to the correct conclusion anymore, but the intermediate steps are still consistent with the mistake itself.
What I mean is that, like, I have on binder paper
Mm-hmm.
what I meant to input,
Mm-hmm.
but just on its way to submission.
Oh, so you copied wrong.
Yeah.
Okay. I see.
You want my paperwork as well as my digital submission? Or?
I think because the submission is an HTML document, you could actually include a bitmap of that too. But now it's past due, we cannot turn it in anymore. Okay, so are there any questions about this particular homework? No questions? All right. So now it's time to talk about the next one. Well, I gotta have something for you guys to do over the break.
Why is extra credit so it's opt in?
No, the idea is to keep you guys out of trouble. You'll be home doing your homework assignment. It's all relative. It's all relative. Okay, so with the homework assignment, we are looking at what I call the omega generator homework assignment. It is due on the 4th, which is the Wednesday after we come back. So it's not the Monday, so you do have like 2 more days or 3 more days, after spring break to work on this one. All right, so we'll take a look at this. Write a single source file program to do the following. Parse parameters of the command line in the following order. The first argument is going to be a base 10 number, that is the number of trials per experiment. The second one is a base 10 number as the number of choices in the first trial. And then the third number is a base 10 number that indicates whether a trial in an experiment is with replacement, which means it's a non-zero value, or without replacement, which makes it a 0 value. Okay, So just this part here, I'm going to give you a skeleton program, and I can upload it too, so you can use it if you want to parse, to interpret the input parameters. Okay, this can be something useful, just in general, general programming, because most of us, are not introduced to this concept in our C programming class. So I'll give you the skeleton of this program here. I will call this one omega generator. So I'll just call omega. And when you define the main function, it kind of looks like that, right? No parameters. But there are actually hidden parameters that are passed, but you can choose to ignore, which most programs do. The first actual argument to main is what we call ARGC, or an argument count. The argument count is basically counting the number of things on the command line when you invoke the executable. Okay, I can further explain that later on. The second argument is a const char star argv. Now this one, you can look at it in different ways. You can look at this. You can look at argv as a pointer to a const char. Okay, but the alternative, or the better way to look at this, is to look at argv as an array of pointers. Okay, it's basically an array of strings. There are actually additional ones as well. I think the environment variables is passed next, but we are not going to use those in this particular program, so we are not going to talk about it. So all of these things are actually passed to every single C program that you have ever written. It's just that we choose to ignore all of these parameters because nobody told you guys that it is actually useful in any way. Is that true or not? More or less? Okay. But in this program, it's going to be useful. So the first thing we'll do in this program is exactly that. Because I want to show you what they are. I want to show you what ARGC is and what ARGVs we are given with. And you go like, but this program doesn't even print a single thing. How is it going to help us? What do you think? Some of you have taken classes from me and you know my favorite way of illustrating how programs work, which is GDB, exactly. So we'll have to do a -G to include debug information. I'll do a warn all and make sure optimization is turned off, that sort of thing. -O. -O allows you to specify the name of the executable, otherwise it's called a.out. So if you don't specify -O, it is by default a.out. And then you specify the name of the source file, which is omega.c, and compiles without a problem. Then you say gdb a.out to debug the executable. And if you do a list, it shows the entire program. So my objective is to take a look at what is ARGC and ARGV. So I'm going to put a breakpoint on line 3 right before it returns, and then I'll run the program. If you run the program with no argument whatsoever, ARGC is 1. It is not 0. So we'll take a look and say, how come it is 0? How come it's 1? ARGC is in fact a 1, not a 0, even though I did not give it any arguments to the executable. So now the curiosity is going to say, okay, well in that case, what is ARGV 0? Because if ARGC is a 1, if count is a 1, that means there's one element in ARGV, and that one, the first element, has an index of 0. So we want to look at ARGV bracket 0, and it turns out to be the path to the executable itself. This is true for every single C and C++ program. It knows where itself is. Okay, which can be handy, can be useful in many cases, because out of this path here, you can now start to say, oh, okay, I can expect my configuration file to be in a subfolder, and so on and so forth. Okay, so that can be helpful by itself. All right, so we'll go ahead and run the program again. Actually, we want to run it this time with a few other arguments. So we'll run it as, okay, what is this? Okay, and of course I have to say this in an Iraj way. What is this?
And then he says something.
Hmm?
And then he says something
Yep. And then we'll give it a number like 1, and then we'll give it some usual switches in Linux, -R for recursive or something like that, or something like recursive equals true or something like that. Okay, so we'll run this. Okay, and this time we'll print. Okay, you can see argc is now 5. Now let's count. Okay, what is this? Is quoted, so it becomes one single thing. Okay, if you use double quotes or single quotes, it becomes just a quoted string, and it is considered as one argument. 1 itself is one argument. -R itself is one argument. -- recursive equals 1 is one single argument. So that's why we are seeing 5, because we got 1, 2, 3, 4, and then the path to the executable itself that makes 5 arguments. But if you don't believe me, you can always just print them out. Okay, we know that one already. This one is the entire string. This is just the number, but the number is not interpreted as an integer. It is a string. It's just a string. And then here's the -R, and then here's the last one, which is -- recursive equals 1, because it is contiguous. There's no space in between, so it is considered as one single argument. Is that okay? Is anyone introduced to argc and argv in your other classes? No? Okay. Well, if you're only running your program from code blocks, this is not going to be very helpful. But on the other hand, if you're writing commands that you are expecting scripts to run, and you want to specify parameters and whatnot, this is really helpful. Okay, so given that your program can take parameters like this, now we go back to Omega and go like, okay, so what would be the first thing that I need to check? I need to make sure that argc is at least 4. Does it make sense? Because you have to give it 3 numbers, okay? So we say if argc is greater than or equal to 4, or if you want to be strict, you can make it exactly 4. So this one is kind of up to you. Okay, so the way I do things is if I have an if, I usually would attach an else, okay, and I'll figure out what to do when the condition is not true. In plain C, I'm gonna use stdio or standard in out. So here would be a good time to print out an error message. So I can just use printf if I want to, but that's actually not the standard way to do things. So I want to use fprintf to standard error. So this way it is going to a different file descriptor as opposed to standard out. Okay, and the message is going to be expecting exactly 3 parameters. Okay, something like that. Or if you want to be more clear, you can say given this many. Okay, and then just report argc -1. Okay, so the message is a little bit more helpful. And also using Unix standard, I want to control the result of the entire program. It is by default a 0, which means everything was okay, but now I'm going to say result equals to 1. And then when I return, I'm going to return result. This is also a standard in at least Unix and Linux. Is the exit code of a program typically indicates whether it exited normally or not. An exit code of 0 means it was successful, nothing special to report. Anything that is other than a 0 means no, I did not terminate normally, something happened. Yep.
Couldn't you just instead at the end of the else statement put return 1?
But then you'll be using a return statement in the conditional statement.
Well, right, but after you hit the else, you're going to stop the program anyways, right?
After you hit the else, maybe, maybe not. So I usually do not put a return inside the conditional statement. There's only one single return at the very end of a function. So even though the syntax allows it to happen, I don't do that.
At least in main, right? Like if you're doing like smaller functions, like other functions, you would put returns in statements, or would you do a different style?
I would do it the same style, which is one single return at the very end. Yep. because there could be extra code that you want to do here, even though you're not giving the right inputs. Maybe there are defaults, right? So maybe there are defaults that you want to assume and say, okay, without anything actually specified, these are the defaults, and go ahead and do something anyway. So I'm not going to do the return here. All right, so now that we have argc equals 4, it is time to interpret the strings as integer numbers. So that means, somewhere I need to store the parameters. This is another trick that I like to use is, if you have a group of things that are actually related and they should be treated as one thing as a whole, make a structure for it. Okay, structures are free. As in, when you define a structure, it does not take up any space in the executable. It is really just saying, okay, these things belong together. That's all it's saying. So I can say, okay, here's a params in the structure. Now, obviously, you don't have to do things like this, but it's just that, if I'm doing it, I might as well, do it the way that I want to do it. So you can say unsigned number of trials, unsigned trial 0 number of outcomes. And then the last one is just a Boolean, but in plain C, there's no Boolean type, so it has to be an integer or unsigned, something like that. So I'm just going to use an integer here to indicate whether it is with or without replacement. If it is non-zero, it is with replacement, so I'm going to call the name of the variable just with replacement, which implies when it is non-zero, it is with replacement. Is that okay? The struct definition itself is not going to use up any space. So we can just basically define structs, everywhere, but it's not going to cost you anything. Question? Oh, okay. Now, because the parameter seems to be related to the entire program, there's the temptation to make a global variable out of the params. Don't do that. Okay, if you can avoid the use of global variables, avoid the use of global variables. Why?
Don't know if they're going to get changed or not. There's enough time they're not supposed to be changed.
Because if you
be accessed all the time.
exactly, everybody has access to all the global variables, so you can no longer look at the call to a particular subroutine to know whether it can potentially change something or not. That is the biggest problem with global variables. If you have a function and you pass a pointer or pass something by reference, yes, then the subroutine can change something. But you know what it can change because of the parameter. You can look at the function call itself and say, yep, this particular subroutine can change that array or that structure and whatnot, but not anything else. So that's the idea of not using global variables. The only global variables that I do recommend people to use are constants. Because constants are supposed to be read-only anyway, so it's okay to be global variables because they are supposed to be shared. Cool. Okay, so now we have that as a local variable, so struct, params, and I just use lowercase params as the name of the variable. Okay, so now we'll go ahead and try to interpret those things. You can combine all of these into one single long line of code, or you can break it up. It's up to you guys. So I'm gonna break it. I'm gonna use one single long line. Okay, so I'm gonna use open paren here, and when you see me do something like that, that means it's gonna be a long expression. Okay, so there's a function called scanf. Okay, that can interpret characters into whatever type that you want to specify, which is kind of the same thing as cin, the greater than symbol of cin, except this one requires a format string, and you can say, okay, what type of number you're trying to read, and what is the base that you're reading from. You can use base 16, base 10, octal, that sort of thing. Okay, so we'll do a scanf, which stands for string scanf. With a string scanf, you have to supply the string itself. So we know arg's v bracket 1 is supposed to be one of those arguments, and then you have to give it a format string. The format string in this case is going to be an unsigned number. So %u, specify, an unsigned number. %d is signed decimal. %u is unsigned decimal. And then you have to tell it the location of the variable that is supposed to store that. So in this case, it's going to be params, which is my variable of the type params with the uppercase P. And I cannot remember my own homework assignment, so I'm going to look it up. The first one is the number of trials per experiment. Okay, so this would be num trials. And that concludes the first scanf. Scanf, excuse me. All the scanf family, every single member of the scanf family of functions returns an integer. The integer tells you how many things it was able to parse successfully. In other words, your format string can be %u, comma, %d, comma, %u again, and it will try to interpret the string, which is the first argument, as exactly that. And then you have to pass it multiple addresses because it now has multiple things to put back into the variables. But in this case, I'm only asking it to read one single thing, which means the only correct answer or the correct return value from this is a 1. If it is anything other than a 1, that means I have failed. Okay? So I'm going to check that here. So I use a extra parentheses here and say I need this to be a 1. Okay? If this is successful, we'll go ahead and read the next one. So the next one is also an unsigned integer, and that one is representing trial 0 number of outcomes. And I want that to be successful as well. And then the last one is going to be a signed integer. So that one has to be read into with replacement. So if all of these are true, then the whole conjunction is going to be true. That is when I say, okay, we got every parameter that we need, so we can now proceed to do something that we need to do. So over here, put your code here. Because at that point, you have all the numbers that you need. But with every single if, that should be an else. So now we can say, okay, I'm not going to be spending a lot of time here. I would just say that failed to parse the necessary parameters. And of course, this error message is not extremely helpful, but it's okay because that's not the focus of this particular program. So I would just kind of leave it like that. There's some kind of output, good enough. So are we doing okay so far? And because it is because it is an error situation, I'm going to turn result to another value. Let's say a 2. So you can either use pound define or enum or something like that to enumerate all the possible ways that the program can fail. Okay, but that's kind of not really the main point of this program, so I'm not going to push that too much. So are we still doing okay with this particular code? So at this point, okay, I'm going to go in here, and you can say, printf, okay, number of trials. In other words, okay, let's not do that. Let's just do something here. Let's see. Okay. I'm just going to call omega from here. So I'll just call omega with the parameter. Okay. So I'm just going to call omega with params, passing it by value, and then you can put your code over here. So omega struct params param. Okay. So that really simplified your job because you don't have to read my main anymore. You can just put all your code in omega. Is that okay? Sort of. Okay. I'm going to save it. and double check that it works, okay? Because I'll be surprised if it does, because I usually introduce some stupid error somewhere. Okay, so we'll do a gdb a.out. And you can also use a breakpoint on the name of a function itself. So that means as soon as the function is called, it will stop in the subroutine. So I can do a b omega or put a breakpoint in omega. And then when I run the program, I can specify 331, okay, which means let's make it 341. So that means we have 3 trials per experiment. The first experiment has 4 possible outcomes, and with replacement. Okay, so I'm going to try this out, run it. We are now at the breakpoint because omega itself is empty. It doesn't do a single thing, but it does allow me to print the parameter itself. So if I print param, it tells me whether the arguments are parsed correctly. So number of trials is 3. The total number of outcomes of trial 0 is 4, and it is with replacement. So I did parse all the parameters correctly. So you can make the assumption that this part is already done, and you don't have to worry about that part. Is that okay? Cool. So you guys will have to take it from here. So I can tell you that there are several ways to do it. You can have the number of trials is unlimited. It can exceed 26 because if it is with replacement, I can say the first trial only has 2 outcomes, but because it is with replacement, I can say you can have up to 30 trials, 40 trials. It doesn't really matter because once it is with replacement, the number of outcomes in the first trial doesn't really matter anymore. Is that making any sense? I just want to stop people from making a nested loop that has 26 levels. Because that's one way to do it. And obviously not a very flexible way. So now that the shell of a program is done, I'm going to upload it. Okay, so I'll upload it first, and then we'll continue to talk about what you do with this program. Okay, so let me upload it first. Where should I upload it to? I'll upload it to the module itself. The reason why I'm not uploading to the homework assignment itself is because Canvas is known to lock the description of a quiz question. Once you open the quiz questions can no longer be updated. So if I want to fix something, I can't do it once you open the quiz. So I don't know whether it is the same thing with assignments. So I'm just going to make that assumption. So we'll just go ahead and include a file here. I'm just going to add a file. So we'll go add a file. And it's going to be a new file from the temp folder called omega.c. Open. And yep. So now you have omega.c as a link to a file in as a -1. Okay, let me just double check, is it the same file? Yep, it's still the same file, so it's still good. Alright, so you have this resource available to you, and I strongly recommend that you start with this file. Otherwise, unless you really feel like doing your own parsing and stuff like that, have your own way of doing things. That might apply for people who want to insist to use C++ instead of C. Because I don't know how well you can use printf and scanf, that sort of thing, in a regular C++ program. You might be able to do it. I think it does not conflict with C in, C out, and that sort of thing. It doesn't conflict with streams. All right. So with this out of the way, the main difficulty is going to be the writing of a subroutine that can generate all the possible outcomes, right? So how would you do that? Or I should ask a different question. How would you start? I'm going to put omega generator to right after counting, because that's a clue. What kind of a clue is that?
You know how many possibilities there are?
Which module gives you the information to work on this homework assignment? It's in the module called counting. All right. So we open it. We open up the module, okay, and we say, okay, how is this helping me? Section 2 only talks about the terms. Section 3 talks about general counting, but it is the first part only deals with replacement, okay, and it doesn't talk about, and it does talk about how to generate the set of all possible outcomes. It is the Cartesian product like this, okay. So the next question is, do you want to write a program that stores every single possible outcome before printing those outcomes, or are you going to print as you generate the outcomes? What do you think?
Print as you go.
Huh?
Print as you go.
Print as you go, exactly. So you do not need to store all the possible outcomes. You just kind of generate and print as you go. Okay? All right. So this is the easier part, okay, because you can obviously use a loop or nested loop to do it. And anything you can do with a loop, you can always do with a recursive algorithm. The part about without replacement is more difficult, because the general equation is this. Okay, let me focus on the part that I want to talk about. Nope. There we go. Okay, so this is the stuff that we want, because the earlier part only has to do with counting, but it doesn't look at the actual set of all possible outcomes. This is the part where you have to look at this and go like, how are we converting this description here into a program? Okay? This is the beginning part. And how do we stop the recursion? This is how we stop the recursion. When I is 1, then you stop the recursion. Whatever is given to you as a set of possible outcomes is your possible outcomes. Is that okay? So when I is greater than 1, then you say, okay, we have to do it the recursive way. You have to basically look at every single element in T, which is passed to you as a set, as an argument. You look at every single element in T, and then you say, okay, I'm going to pick that element as my first outcome, okay? And then you do a Cartesian product with the rest. The rest is a recursive call. Are we doing okay so far? Sort of, maybe, okay? But you can see how this can turn into a recursive subroutine, but it needs a loop inside the recursive subroutine, because you have to say, I'm going to go through every single possible element in the set, and when I find an element, I'm going to do this. Are we doing okay so far with this? Do we know how to pass a set as a type? Okay. Do we know how to scan a set of all possible elements? You only have elements from 0 to 25, okay? So you can always use a loop and say for I equals 0, okay? I is less than 26, I is less than 26, and not element found, and then you just do a plus plus I as the post operation, and then inside the loop itself, you just keep asking, is this I in this set? Nope, move on. Is this I in this set? Nope, move on. Oh, this I is actually in the set. Do something about it. Is that okay or not? Do we know how to enumerate? Do we know how to go through all the elements in a given set? Knowing that all the possible elements start from 0, it ends at 25. Okay? So the next question now is, if you get down to omega 1, then how do you print out everything? So I'm going to give you an example. Okay, we'll go to here, and then I'll give you an example. So I'm going to say omega. Okay, so we have omega of, I'm going to pass the I, as a parameter too. So in addition to the set, I becomes a parameter. So omega, let's say this is 3. Okay, so we have 3 trials from this point, and then the choices that I have at this point are A, B, C, D. Okay, so what do I do? Remember the big union thing? Okay, so this big union thing, the big union thing is indexing on elements of T, right? So that means this boils down to A. Okay, so it boils down to this thing, Cartesian product with omega of two trials left, and then only B, C, D left. Okay, union with B, Cartesian product with omega again, only 2 trials left, but this time is A, C, D, because B is the one that is chosen for this level. Union with, in this case, C times omega of 2, and then this time is ABD, ABD. And then the last one is I choose D as my own outcome, and then omega 2 ABC is going to be all the possible outcomes for the next 2 trials. Is that okay? I'm just expanding the union notation with a very concrete example. Is that okay? So with the first recursion, which is ohm to BCD, what's going to happen? Ohm to BCD, it's going to look like what?
The Cartesian product.
Okay, so it's going to be B, Cartesian product with ohm of 1, right? And then CD itself, okay? Union with, okay, I forgot about the union. So we say, okay, I'm going to be lazy and just use that as union. Looks close enough. And then we say this is C times ohm of 1, BD, right? Union with D. Okay, this part is really kind of boring. 1 and then C, B, C. There we go. Wrong notation. So there we go. All right. Is that good so far? Well, let's look at ohm 1 of CD. So we look at ohm 1 of just CD. That is really just CD itself, because this is the only trial left, right? So are we okay in terms of breaking down the recursive algorithm step by step until we get to the point where we do not do any further recursion, we stop the recursion? Okay. So now the question is, what are you printing at this point? So you print A, B, and then over here, C. Then you have to print A, B, D. Then you're done with this recursive step. You go back up 1 level. So now you handle ohm 1 of BD. So I'm going to write it down here. Okay. So at this point, you want to print A, B, and those 2 are from the earlier parts of the recursion. And then your choices is a C versus a D at this level. Is that okay? Okay, so you don't want to do any printing when you're in ohm 3 or when you're in ohm 2, but you do need to do something to let the later invocations to know that, oh, the first invocation has currently chosen A, the second invocation currently has chosen B, now you can choose C or D. So somehow that information has to be passed on to the next invocation when you do the recursive call. Is that okay? And once again, I don't want to suggest the use of a global variable, even though it is quote unquote doable. It's not a very good idea. So you can just kind of pass something along, okay, as a string, for instance.
It's funny because Araj uses global variables.
Huh?
Sabzavar uses global variables sometimes. So you tense up there.
No, I'm not. I'm not tensing up. I'm just gonna do this, and I'm not even religious. So. How about this? I'll do the pound sign. There we go.
Hashtag.
Yeah, hashtag. The pound sign is, by the way, the symbol for comments in most script-based languages, like in Bash. The pound sign begins a line of whatever is to the right-hand side of a pound sign is are comments. So I do this. Global variables.
Comment them out.
Yep. So, but you need a way, okay? So you just need a way so that earlier invocations of the recursive call sequence can store what they have chosen as the entire family of outcomes, okay? So I'm gonna finish this too. I'm not gonna finish the entire thing because that's gonna be really long, but I can go back up one level because the next level is going back up to here. Okay, I'm done with the B, everything that starts with AB. So I'm going back to here. So I'm going back to this part here to handle the C and then ohm1 BD. So that means the next call is going to be ohm1 with BD. But in this case, the earlier invocations would have chosen A and C in this case. So when you're down to the part where you're not doing recursion, then you have AC already chosen by earlier invocations, but you can choose B because B is in the set given to you. You can also choose D because that is also in the set of possible outcomes that you can choose from. Is that okay? Then you go back again, and this time we're handling D times Cartesian product with ohm1 BC. So that means the next call is going to be ohm1, and then in the set you don't have BC left. Okay, and we are not going to do any further recursion. So that means the set of all the possible outcomes is really just B and C to this invocation. And at this point, the first invocation is still choosing A, but the second invocation, because we are already on the third iteration of the loop, the second invocation has now chosen D. So now you can choose your B, you can also choose C, and that concludes everything that you can do at the bottom level and also at the second level. So when you return from this ohm1 BC, you go back to here, but there's nothing else to do in the second invocation also, so you go back to the first invocation. At that point, when you go back to the first invocation, the next thing you need to handle is going to be this one. Does that make any sense? In other words, you're going all the way back to the first invocation of ohm, and the first invocation says, okay, I have exhausted everything where the outcome of my first trial is an A. I'm going to explore the second possible outcome for my first trial, which is B. And then it will remember that B is already used, so whatever you have to do next can only choose from A, C, and D, and there are only 2 trials left. So then you do the recursive call again. The recursive call is going to call your own 2, and then this time it's going to be A, C, D instead of B, C, D, and then it keeps going again. So the key is one, you have to keep track of 2 things, when you're dealing with the recursion. One is how many trials are left. Okay? When the number of trials left is 1, then you don't need recursion, you know how to deal with it. Okay. The second thing you need to track is what are the outcomes that are available to me. That will be the set that is passed to you. But when you do recursion without replacement, then whatever element you have chosen for that iteration needs to be removed from the set so that further trials no longer can consider that as a possible outcome. Is that okay? The third thing you need to pass is a string that basically remembers which trials, which recursion or which level of recursion has chosen which outcome. So that way, by the time you get to the very last, when you get to the end of the recursion, it knows that the earlier invocations have chosen what characters, and then the last invocation only has to do with the very last character of that string. Is that okay? This is the best I can describe it without actually writing the code.
When is this due?
Huh?
When is this due?
In 2 weeks.
Oh.
Okay.
In 2 weeks minus 1 hour and 10 minutes. So we got the rest of this week,
Yeah.
spring break, and then two
Okay.
and a half more days after spring break.
Would you respond to any emails over the break?
Yeah, but probably not very instantaneously. So are there any questions about this log here? Because this is me attempting to run the algorithm by hand to show you, how parameters are passed and what you need to take care of on a per invocation basis. I cannot give you the actual code, but this comes close. Is that okay? Okay, so we still have 10 minutes left, so I'm going to show you some interesting techniques of recursive subroutines. Okay. Okay, so I'll just call this recursive, and we'll give it something like a structure. I like structures. And we'll give it an integer x and an integer y. Okay, it doesn't matter what this has. And then we'll have main, and we'll initialize a structure first. So main has its own structure, struct x. We'll call it. I'm running out of names. A, okay. And then we'll say a dot x is 5. Okay, I said 5. Okay, here's the fun part. Okay. So a dot y is 0. A dot previous is null. Okay. Null is also known as 0, by the way. Okay. So I have initialized one instance of the structure, and now I would write my subroutine here. So I'm going to write my recursive subroutine as I don't know. Let's call it f here, and it is expecting a. I'm thinking about pointer to a structure or structure. Let's make it a pointer to a structure. So struct x, p, x. Okay. And here I'm doing the recursive call, f of the address of my local variable a, which is already initialized at this point. Okay. So, as any type of recursive subroutine, I have to do an if. Okay. Well, I'm gonna make it even more fun. Let's turn it into a for loop. Okay, so we'll turn it into a for loop where we can log into whatever px has, and okay, there's no initialization, so px we look at the variable or the member x. So as long as member x is non-zero, we will perform whatever operation that needs to be done, and then do a minus px x in this loop. And then in this loop, we're gonna do a recursion. But instead of doing just that recursion, I'm gonna do this: struct x a again, And then we'll say A equals whatever Px points to. And then we call itself with the address of A, not X. Okay. And of course, we also need we need to stop the recursion somehow, right? So we'll say if Px x is 0 to begin with, that's the end of the recursive subroutine. Hmm?
Forgot the X.
Ah. And I'm just fixing the indentation level here. Okay. So this is going to be the fun part, because now I actually have a, oh, I don't have a linked list yet. I do. Okay, there we go. So now we have, I'm using the recursive subroutine to set up a linked list to go back, all the way back to the first invocation, back to the root of the entire thing. So when Pxx is a 0, I'm going to stop the recursion, and I can track my way backwards to figure out the x value of all the previous invocations. So we'll go ahead and we'll give it a try, right? Struct x ptr is px itself, and then we'll say as long as px is non-zero, non-null, do the following, and we just say print %d \n px x, and px gets px previous, and we don't need the \n at the end of this loop. Then we print the \n. There we go. So the loop here allows me to track backwards. In other words, I'm not only looking at the structure that is passed to me, because that thing points to the one before that. I can actually track down, everything along the way until I find the very beginning. Okay. Okay. Include stdio, and that should be it. Okay, let me see if it compiles. gcc-g. Oh, it does compile.
Said that before.
Oh, segmentation fault. Okay, fine. Okay, so this is another thing that is kind of nice, when you use a debugger. When you get a segmentation fault, at least it will tell you where it is doing a segmentation fault. It is on line 10 of recursive, in recursive.c. So we say, okay, what is on that line? So line 10 is at the very beginning, and we're trying to dereference px. So what is px? Cannot access memory at this location. I think I know why. I used up all the entire stack already. I did not change the one thing that it needs to stop the recursion at some point. Okay, so, oh, there we go. Okay, when I perform the recursion, which is down here, you can see that I did not change px points to x is not changed when I pass it on to the next one. So that means, if it is 4 or 5 to begin with, it's always 5. And that's why it keeps doing the recursion and it never ends. So that means, a dot x has to be decremented by 1 for it to have a chance to actually stop. Okay. There we go. By the time you get to the entire chain of recursion, the value of x, the member x inside the structure has to be 0 because that's the reason why I stopped the recursion. But it can track backwards and find out that, oh, the previous invocation, the x of the structure of the previous invocation has a value of 1. That one, the other one has a value of 2, value of 3, value of 4, and then the last one, or the first one, has x in the member x initialized to a value of 5. So this program doesn't do anything actually useful, but what it does do is to illustrate the fact that I have a way to go backwards. The last invocation of the recursive chain has a way to track backwards and figure out, okay, oh, this is the structure of my previous invocation. It has got this in this particular member. The previous one has this, and then the previous one has this, and the previous has this, until it gets all the way back to the very first invocation. So, do you have to use something, obscure like this? Probably not, okay? But you need some way so that you can pass information that is set by an earlier recursive call to a later call in the same recursion chain. You can use an array, you can use something like this, back pointers, but you need some way to do that. That would be the part where you print what the earlier parts have chosen. So in this particular algorithm, by the time you print ABC, the C is the one that is chosen by the very last, the end of the recursion. A is chosen by the first invocation. B is chosen by the second invocation. So now the question is, by the time you print, how did you know that the first invocation chose A, the second invocation chose B, and you are the one choosing C? That is the question. Okay? Instead of using back pointers and linked lists and stuff like that, there are other ways as well. There are easier ways to do it. You can just pass a string, okay? And I'm not going to say much more than that, okay? You can pass a string, and you can go with that run. You can run with that one. So, whichever way you choose to do, the program is like that. So at any time, you really do not have to store the gazillion outcomes. You only have to keep track of the current outcome that you're trying to generate. So the memory storage requirement is actually not that much. And I highly recommend using recursive subroutine to do it, because otherwise you will have to kind of maintain your own stack, which I think is actually more work than doing it recursively. All right. Do you guys want me to upload this program too? Are you sure it's not gonna make it even more confusing? Okay, I'll upload it. All right.
To be the judge of that.
Yes, I'll let you guys evaluate. That's correct.
What is the program supposed to show
Which program?
that we have to fit to?
It's supposed to show all the possible outcomes. There are examples included in the homework description of what it is supposed to generate.
Oh, okay.
Mm-hmm.
I just have a question. So I know like last time we talked about representing a letter with like a bit.
A bitmap representation.
Yeah, I'm kind of confused. How do we assign a letter to a bit?
Okay, so the letter is really only for printing purposes.
Okay.
So element A is nothing more than element 0, element B is element 1, and so on. So until it is time to print, you just have to know that they are known as 0, 1, 2, all the way up to 25.
Okay, and that's gonna be the number of bits, right? 25 number of bits, or?
The representation that I chose is a 33 integer,
Okay.
so you can actually have up to 32 elements, but of which we only need 26.
Okay. All right, thanks. I'll try to work on that.
Okay.
Yeah.